So now I leave the floor to our last speaker, Zhiwei Zhen from the University of Texas at Dallas in USA. Welcome, Zhiwei. Hi, Zhiwei. Can you speak? We don't hear you. Oh, we don't hear you.
Hello? Can you hear me?
Now we hear you. Yeah, excellent.
Yeah,
Thank
okay.
You so much.
Yeah, thank you, Ignacio, for the introductions. My name is Zhiwei Zhen. I'm a PhD candidate at the University of Texas at Dallas. Today, my topic is geometric deep learning to visualization, uncovering hidden patterns in climate-induced biosurveillance and resilience. This work is being supported by the NSF grants and NASA grants. This work is a joint project between UT Dallas, NASA Jet Propulsion Laboratory, Temple University, Baylor University, University of North Carolina at Charlotte, and Utah State University. So, since COVID-19 spread around the world, there has been reported 479 million confirmed cases and 6.12 million deaths as of March 26, 2022. There are already some studies trying to track the linkages between the atmosphere variables and how the COVID progress. Also, we suspect that there may be a linkage between the ambient air quality and the COVID-19 mortalities. In this project, we aim to get a deeper insight into the relationships between the atmosphere variables and the socio-economic factors with the COVID-19 clinical severities. For the outcomes, we propose geometric deep learning models which investigates the potential atmosphere conditions and the socio-economic variables, how they will influence the COVID-19 clinical severities. We conduct our experiments in 3 US states, California, Pennsylvania, and Texas. The first motivations of our project is the relationship between the atmosphere variables and COVID. Right now, the existing studies find that the calm, cold, dry, and overcast conditions are favorable for the COVID-19 transmissions. There are also studies find that the temperature 13 to 19 Celsius degrees and humidities in 50 to 80 are favorable to the COVID-19. Also, the precipitation may influence how COVID-19 spread. Even though we have some studies on the work, but most of those studies lack the uncertainty quantifications. Also, few of them have considered the socio-economic variables. For us, we want to add more certainty quantifications in our studies and also involve the socio-economic variables. Our second motivation comes from the power of the deep learning models. In addition to the prevailing math and the statistical approaches, there has been some attempts trying to do the COVID-19 forecasting with deep learning models. But a few deep learning models try to integrate the covariates. For example, the Google Cloud AI and the Harvard Global Health Institute collaborate. They do the COVID-19 forecastings with the information from economics, demographic, and hospital resources. Also, the Google Trends is a hybrid models that involve some covariates. But we find that most of the current existing models, no matter they are math models or deep learning models, they don't involve the nonlinear relationships between the atmosphere conditions and the COVID-19 clinical severities. So here we also want to bring the atmosphere and the socioeconomic variables in our deep learning models. Our third motivations comes from the an interactive way to monitoring the COVID. There are numerous visualization systems developed for the COVID-19 monitoring. For example, the Coronavirus is a system that provides an interactive views for us to view the spatial temporal COVID-19 variables. It also provides location and feature-based filtering. Another system, GeoAuditive, they provide us the exploratory analysis of clinical, socio-economic, and environmental data for COVID-19 targeting. However, to the best of our knowledge, those systems do not support incorporating the cross-domain data for analyzing the impact of COVID-19 severities. So we are to propose our own visualization system, which can give us a way to do the cross-domain data analysis with the geometric deep learning models, which integrate socio-economic and atmosphere variables. We bring the following question into our research progress. Does the information extracted from the satellite observations, like the humidity, temperature, and AOD, will exhibit any predictive utilities for the COVID-19 forecasting? Whether regional socio-economic variables, like the pollution related to the COVID-19 mortalities, how can we use the visualization systems to better analyze COVID-19? And can we use the climatological annual circles in temperature, humidity, and AOD to model COVID-19 dynamics? We believe that the answers of those questions can contribute to the decision makers to better allocate the medical resources. So in order to analyze analyze the COVID-19, first step, we collect the NASA satellite data sets, which composed of two parts. The first part is atmosphere infrared sounder, AIRS, and second part is moderate resolution imaging spectral radiators, MODRS. So the AIRS, this data set provides us the air temperatures and relative humidities, while the MODRS provides the iris optimal depths. So with those environmental variables, our hypothesis is that the local hotspots of a relative high AOD, like the poor air quality, may increase the risk of COVID-19 clinical severities. We also hypothesize that the COVID-19 severity may be related to the annual circles of temperature and humidities. So here we show some examples of how those environment variables are distributed in United States. For the COVID-19 data sets, we use the daily records of COVID cases, hospitalization, and deaths. We get the time series from official state and county dashboards. We get our data from the United States Census Bureau, COVID Act Now, and MIDAS. We mainly focus in the following 3 US states, California, Pennsylvania, and Texas, since they have different policies for handling the pandemic. We also use the county level connections network in each state. So with those COVID data and our environmental variables data, we use a graph representation method of those data sets. Here we aim to construct spatial temporal networks. And in the networks, each graph composed of 3 components: the vertices, the edges, and the adjacent matrix. The vertices are the node sets. Each node represents a county, and the edges here represents the connection relationship between those counties. For example, the connections can be based on the official county adjacent field record layout. If 2 counties share the boundary, we can see that there's connections link them. And the adjacent matrix is constructed based on the edges. The future matrix are generated using the environmental variables, since that our environmental records are based on county level. So we can have our, we can assign those features to each county, and also our hospitalization rate, the deaths and the cases are also based on county level. So those values can be used as the features. With our networks and the feature matrix, our goal is to predict the future features. For the models, we use the geometric deep learning. Geometric deep learning is a branch of deep learning which is specifically designed for the analysis of non-Euclidean objects, such as graphs and manifolds. It captures the heterogeneous spatial temporal patterns while learning graph structures. So it improves the model performance compared to the traditional deep learning methods. And most recently, it emerges as an alternative tool for the spatial temporal forecasting and anomaly detections. For comparison purpose, we also benchmark to other kinds of neural networks, the recovery neural networks and the graph convolutional networks. For the analysis, we focus on the consensus analysis, especially the adding walls at county level. We will run our models with environmental variables and without environmental variables. If we see a significant improvement after adding the environmental variables, we will count that county in our adding walls, which means that the atmosphere variables do help improve the model accuracies. All the model performance are measured using RMSE, reduction of the root mean square error. So why use graph neural networks? There are two reasons why we use graph neural networks. First is that graph neural networks allows us to capture the nonlinear relationships between variables. Here we can see when we calculate the nodes with embedding at L+1 layers, we use the nonlinear activation functions with the trainable parameter and the normalized Laplacians, such that compared to the traditional statistical and math models, it has more abilities to capture the complex nonlinear relationships between variables. And secondly, it involves the graph structures in the calculation. We see that it only considers the nodes with neighbors and the V itself when doing the calculations, such that it can fleet out the noise in the calculations. For us, after we use our graph representation width to get our climatological features and our dynamic networks, we can put them into our geometric deep learning models to get the output. We can also use only the climatological features without the dynamic networks and put them into the traditional deep learning models to get the results and do the comparisons with our geometric deep learning models. To the best of our knowledge, there are no previous attempts to use the consensus among multiple RNN or GNN models to characterize the impact of atmosphere factors on COVID-19 clinical severity, along with an interactive visualization system. For the experiment settings, we use two kinds of connections. First, we consider the board-based county connections, which is built while the official county adjacency file record layout. So if two counties share the boundary, we consider they are connected. And we also use the socio-economic based county connections. So a socio-economic based network for each state is constructed using 9 socio-economic variables. And if two counties share the similarities in the in those socio-economic variables, we will consider that they are connected to each other. We perform our experiments in 8 types of geometric deep learning models. And for the data sets, we use the daily data from February 1st to December 31st, 2020. We use the first 80% as our training set and the last 20% as our testing set. After getting the experimental results, we plot the model votings using AOD and the AOD map. Here we find that the AOD values do help model to improve the performance in the Northeast Texas and the Great Houston areas. And if we also plot the AOD map, we can find that those areas where AOD do help improve the model accuracy is also the areas with the high AOD map. So those high AOD map usually refers to a bad air quality. So we do think that the air quality will influence how COVID-19 spread. After getting inspired by the results of the AOD voting and the AOD map, we designed our own visualization systems, which compose of following parts. Firstly, it shows us the voting summaries. Here we can see that the counties where the environmental variables do help are marked in blue. And we also have a table shows that how many counties where environmental variables can help. We have the summary information here. Meanwhile, it provides us the values of the hospitalization rates, the AOD, relative humidity, temperature, socio-economic status, households composition and disability, and minority status and languages. It can show us the values of all those variables. And it can also show us our networks. So we can see that here each node is represent one county. We can see how those counties are connected to each other. So for these systems, we can also try to adjust how the networks are constructed here. For example, here the distance threshold allow us to change the number of edges in the dynamic network. The network strength will change the size of network showing below, and the network centricity threshold will change the counties we focused. It has give us multivariate visualizations with the atmosphere impact variables. Also, like it can show that the GDL votes, which means that where models do improvement, the impact variables, and which connections we use here. Here, I will show an example of how these systems works. So, for example, when the threshold is very low, we have only a few edges. And if we increase the threshold here, we will have more edges appear. And if we increase it, there will be more and more edges appear in network. We can change the way how we construct our networks. And if we look at the hospitalization rate here, we find that the area near El Paso, near Houston area, and the areas in the northeast part, those parts are with a higher hospitalization rate. And those areas are also the areas which shows the similarities in the socio-economic variables, which are marked in the deep blue. So we find the similarities between the socio-economic status and the hospitalization rate. In the network, those counties with similar socio-economic variables are also connected to each other. And if we look at the AOD values here, we can also see that in Houston and in Northeast Texas, those areas are with higher hospitalization rate are the areas with the high AOD map. Yeah. So with these tools, we can do many other ways to try to explore those visualization system, and we may get more inspirations about how the environmental variables can influence the COVID-19 spread. So in general, we conclude that a larger proportions of the deep learning models agree that the COVID-19 hospitalizations in northeastern Texas and Greater Houston are impacted by the high AOD rates. This phenomenon may be attributed to the higher than average number of unhealthy air days in these counties. And Texas tend to exhibit higher sensitivities of COVID-19 clinical severities to poor air qualities. And the areas with the high hospitalization rate and low air qualities tend to be often populated by the socio-economic disadvantaged groups. So those results do imply that the need for further analysis of healthy care fairness and environmental justice in those areas. From the visualization system, we see that AOD plays a bigger role than humidity and temperature when linked to forecasting hospitalization numbers. And if we can couple with the weather forecastings, those systems can be used to identify areas of the highest vulnerability risk and the potentially next hotspots, which requires the proactive medical emergency readiness. Thank you.
Thank you so much, Zhiwei. This is a very interesting presentation about our visualization system. That's very important given the current, well, not ongoing right now, but the pandemic issues during last years. This is very interesting. If any of the attendees have any question, please feel free to open their microphone, or you may write it in the chat. Okay, if not, let me ask one question. So you were working on the COVID-19 forecasting problem, but I mean, there are many aspects on this COVID-19 around COVID-19 research. For instance, the problem of detecting infectious disease outbreaks, like in COVID-19 or probably others, can be seen as an anomaly detection problem. Have you tried anything on that trend, on that type of research, like anomaly detection of outbreaks or anomaly detection of something different on the spread of the COVID-19?
Yes, our systems can be applied to not only the COVID-19, but can also to do the other like system diagnosis and like water pipeline systems or the electricity networks. Our system can be also used in those areas, and the atmosphere variables can also be changed into the other kinds of variables if needed.
Thank you. Is there any other question from the audience? Okay, if not, thank you, Zhiwei, for this great presentation. Thank you, everyone, for attending this exciting session. And also, thank you so much for attending our today's session on the TIES 2022 annual meeting. We look forward to seeing you in tomorrow's session. Please remember that our website contains the full program, abstracts, and bios of all the speakers Also, if you miss any presentation, don't worry. We will post the videos in our website for your convenience, and enjoy the rest of the day. See you tomorrow.